to look at this, and we want to be able to know what is the derivative as I approach 1 from the less than 1 side. What's the slopes of our tangents going toward as I approach 1, or x from the, 1 from the less than 1 side. And I want to know what happens as I approach the tangents, or the tangents approach, the slopes of the tangents approach from the greater than 1 side. Okay, so let's start here. Let's say from x approaching 1 from the less than 1 side. Slope of our tangent will be the limit as x approaches 1 from the less than 1 side. Now remember, we're not talking about does the function have a limit there. We're saying does it have a derivative there. So we're going to use what's called the alternate definition. That's one we just looked at. And so we're going to have f of x minus f of 1 divided by x minus 1. Yeah.
Would it work if we used the other equation?
Yes. Yes. And if we did the other one, we just would have to plug in 1 using this function. Well, actually, we have to find actually 2 derivatives, though. Still, using this one and using this one. Okay, so we would still have the work to do. Sorry, doesn't it? It doesn't simplify it at all using the other one. Okay, so let's see. If I'm going to approach 1 from the less than 1 side, again, we just need to know which piece we're going to use. Top one. So we have x minus 1 quantity cubed minus 1 minus 1 quantity cubed divided by x minus 1. And I should have that from the less than 1 side there. Okay. Again, if you need to know how to expand this, I went over in the other class. Have we gone over it in this class? Did we do that on the first problem? We did, didn't we? Expand. You have to help me if I skip over stuff like that. Did we? Okay, thank you. So this would be x cubed minus 3x. I'm going to say plus 3x squared times negative 1 plus 3x times negative 1 squared plus negative 1 cubed. This is just the format that I've used to expand that. If you use your Inspire, you would be simplified before. And then minus 0 and x minus 1 in our denominator. Heather, did I do it right? You're checking it, I assume, so I'm hoping. Okay, so we have x cubed minus 3x squared plus 3x minus 1 divided by x minus 1. You know what? I just made the work a little more complicated. Do you know why? Nothing wrong with what we have on the screen. Well, what I need now to do is to factor this. Okay? So I'm kind of doing a little too much work. Let me just do a little shortcut. Okay? So this is the shortcut. If I look at the limit as x approaches 1 from the less than 1 side, I have x minus 1 quantity cubed divided by x minus 1. Does that look a little easier? Okay, got the quantity squared here and the quantity down here. I would get to the same place because I could factor out an x minus 1, and what's left would be x minus 1 quantity squared. Okay. Can I use direct substitution? And when I do, I get 0. So remember, what does this mean? It goes all the way back to this piece, slope of the tangent, and so, slope of the tangent. So this is the first derivative at x approaching 1 from the less than 1 side. I've got to do the same thing here. I'm going to set it up the very same way. F of x minus f of 1 divided by x minus 1. I'm still going, but no, when I do this part, what am I going to use for f of x? Because I'm approaching it from the greater than 1 side, yeah, I've got to use that second piece there. So x minus 1 quantity squared minus 1 quantity squared divide by x minus 1. We'll use the shortcut on this one. And I end up with x minus 1. Do I get 0 again? Yeah. Yeah. Again, this is the derivative at x being approached by the greater one. Okay, so now, let's go back and see. It says, if it exists. What on earth are we looking at? Yeah, Heather?
Are we looking at the shortcut on the top?
Absolutely. Oh, yeah, absolutely. Does the derivative exist? We know it's continuous there, but does the derivative exist? It does if approaching from one direction, the limit, slopes of tangents, is the same as approaching from the other direction. And so if we look at that, we get the same values. So therefore, f of x well, let's just say it this way. F prime of x is equal to 0 at x equaling 1. You know, the graph of this is going to be, if this is at 1, you know, the cubic curve looks like this, so it's going to be going something like this. And then, you know, what a parabola looks like, and so it's going to be a little bit wider, but at this point we're going to have a slope, a tangent, that's actually going to be a horizontal line, which kind of defies all the ideas of tangency, but because it cuts right through that, but that's exactly what happens. It's going to be a horizontal line there. Okay. Oh, just a few more thoughts here. Describe the input values at which this function is differentiable. And maybe from the back it's hard to see, so let me just see if I can't help you out here. That's x to the 2/5 power. Okay, if you got the notes, you saw that. But describe the input values at which the function f of x equals x to the 2/5 power is differentiable. Is it with this problem or another one? Yeah, we're not doing any proofs of those theorems. Okay, so what I started with on the last problem, Sean K., and I didn't mean to confuse anyone, was I said, is it continuous? And we found out that it was using a review of what a continuity is. But then we had to go through and decide, is it differentiable, because continuity does not always imply differentiability. Then we have a theorem that says if it's differentiable, then we know it's continuous. So the fact that we found that we have a derivative implies also that it's continuous. So we could have just done this discussion, the derivative, and then answer the question, is it continuous? The fact that it has a derivative implies that it is continuous. Okay, so if I just say discuss the continuity of this function, I don't tell you what I want you to do with it, you could opt to find the derivative and say because the derivative exists at 1, by that theorem we talked about in class, if it's differentiable, then it is continuous. Right. So this just says find the derivative. But, we always need to kind of review for the test. So, okay? Okay, let's go on. Describe the input values at which the function is differentiable. Now, this means, and it does have the word the in there, but it has a plural on values. So this means find all the input values at which the function is differentiable. What's an easier question to answer? Where it's not. Yeah. If we can find out if this function is not differentiable someplace, and that's the only place we find that it's not differentiable, then we will assume that it's differentiable every place else. So we're going to do that. We're going to look at the derivative of this function, and we're going to decide, is the derivative ever undefined? If it's undefined at a point, then we know it won't have a derivative there. But if that's the only one that comes up, then we know it's okay every place else. So let's do this first. Let's graph this function first. So we have x to the 2/5 power. So I'm just going to insert another page here. And I've got x raised to the 2/5 power. Okay. Looks very much like another problem we saw, but looks can be deceiving. So we want to make sure, we want to do some analytical work here. Looks like there's what we call the cusp right there, but we want to make sure. The other thing I want to point out is that if you have, as we have x to the 2/5 power, what's another way of writing x to the 2/5 power? The 5th root of x squared. Okay, what's another way? How about the 5th root of x quantity squared? When you raise a power to a power, we have the commutative property. We were multiplying, and multiplication is commutative. So this would be the same thing as x squared to the 1/5. And this would be the same thing as x to the 1/5 quantity squared. We might need to go back and forth between those if we need to think about it. Those ways that we can see it. Maybe one way is easier than another. So I just wanted to point that out to you. We may not need it, but always nice to have options. Okay. Is it differentiable? From our graph, it would appear that something happens at 0. Okay? Let's then begin at that point. So, well, first of all, let's just do this. F of x equals the slope of the tangent. And we're going to, let's build the general. We haven't done that for a while. So let's just build the general one. And remember that's f of x plus delta x minus f of x divided by delta x. So for us, we have the limit, delta x approaches 0. If we have f of x plus delta x, that's going to be, let's look at it as the 5th root, thank you. The 5th root of x plus delta x quantity squared minus f of x, that's the 5th root of x squared divided by delta x.